Good afternoon to you all. Welcome to this session. In this session, I'll be discussing with you on 3D characterization of forest biodiversity. So to start with, we know that three-dimensional forest structure. These are very important driver of ecosystem functions as well as different services. And this structural complexity, when we say structural complexity of a forest, we mean it is all dimensional, architectural, distributional patterns of plants and their organ in a given forest space over a given point of time. This vegetation structure, when I say this, provides a physical environment that generates, supports, and maintains forest biodiversity. Therefore, it is considered as a very important component for forest management as well as wildlife management. Generally, these forest canopies, they mediate a microclimate, and they provide perching, nesting, foraging, and covering habitats of many animal species and influence the food quality, diversity, and accessibility. And the forest horizontal as well as vertical structures. These are identified as the essential biodiversity indicators across a broad range of forest ecosystems around the world. So here in this lecture, I'll be basically discussing with you how these forest structures, these are related to forest biodiversity assessment. So when you say species diversity of a forest, it has been found that it has been positively associated with the vegetation structural diversity as a different vertical strata and structural heterogeneity of forest stand. This provide ecological niches of species of various habitat specialization. So the linkages between forest biodiversity and forest structure are considered as a central assumption of ecosystem-based management approaches in forestry. MacArthur in 1972, he identified like a productivity, climatic stability, and habitat structure as the primary drivers of biodiversity. And this approaches aim at maintaining diversity of forest structural attributes at both landscape as well as stand scale in order to maintain forest biodiversity. So the traditional forest biodiversity measurement these are mainly based on ground-based inventories, which are very labor intensive. Hence, remote sensing techniques have been increasingly being used recently for biodiversity assessment as well as for monitoring at various spatial as well as temporal scales. So there are lectures also with how remote sensing technology can be utilized or can be utilized for forest biodiversity assessment. Now, generally, you can see those spectral information acquired from different optical data sets have been widely used to assess compositional as well as functional components of biodiversity over period over different scales, spatial scales. But habitats classification based on land cover types, habitat suitability indices, and seasonality, these have contributed significantly to the species distribution models. So more defined, detailed, fine scale mapping of vegetation structure is now needed to allow a broader range of biodiversity values to be included in forest management planning. So in that context, light detection and ranging, or we call it LiDAR, this is an active remote sensing technology that can accurately measure the three-dimensional vegetation structure, which, as I said, which is a very good indicator of biodiversity of a place, mainly in the forest areas. So a recent advancement in the laser scanning technologies have allowed us to make the 3D model of forest or the structural components of forest directly from the 3D point cloud data. So large area structural inventories using LiDAR-derived variables they characterize generic habitat structure and are helpful in guiding biodiversity monitoring as well as conservation. So basically, this LiDAR-derived forest structural attributes, these have been widely used for many ecological purposes, like forest vertical layering, overall architecture of forest, identification of various successional stages of forest, then stratification of forest, tree species awareness, of course, volume, biomass, carbon. Most of the studies are based basically on this volume, biomass, and carbon storage, and as well as in vegetation regeneration. So here we have highlighted that like how vegetation structure is important in biodiversity, studies, or forest biodiversity studies rather. So, and to address this or to get an overall view of this structure, light detection and ranging or LiDAR data is the most significant data set which can provide you the structure of a forest. Now, coming to LiDAR, this is basically a technology. These are active sensors, as I said earlier. Also, they're used to work out the height or height of a target. And generally, when we use this technology or this for measuring height of any object, is termed as LiDAR altimetry. Basically, in this, there is it has a laser, which is the device that emits electromagnetic radiation through stimulated emission, in which light of narrow wavelength channels is emitted. So these pulses actually these are sent from different platforms. This could be a ground-based platform, could be UAV, could be aircraft, could be a satellite. So these are laser pulses are sent from this thing to detect and determine a range of objects, and this technology is called LiDAR or light detection and ranging. Now, in this figure, you can see this explain the fundamental concept of a LiDAR. Now, the main concept is you send a laser pulse towards a target, and measure the timing and the amount of energy that is scattered back from the target. So here, from aircraft, you are sending the laser pulses. It is hitting the targets and going back. So you basically you're measuring the timing and the amount of energy that is scattered back. So the return signal time, let's say t, that provides a measurement of the distance between the this object and the scattering instrument and the scattering object. So distance from the sensor to the target can be calculated by using this formula. D is equal to c multiplied by t by 2, where c is the speed of light and t is the time taken for the pulse to return. Now, when you are sending pulses, the care should be taken. Suppose care should be taken, like if all the pulses return from the canopy, this goes back, we won't be able to calculate the height of the tree. So at least few pulses should reach the ground so that we can get a reference point. So the return will be from this point as well as from the ground surface, and using this time delay we can calculate the height of this object. So some laser pulses should reach the ground surface so that we can calculate the height of these objects. Now, there are different types of LiDAR based on, let's say, platform. It could be terrestrial LiDAR, it could be airborne LiDAR, it could be spaceborne LiDAR. So I'll discuss one by one. So first of all, to start with the terrestrial LiDAR. Now, terrestrial LiDAR, as the name itself says, is a land-based laser scanner, which in combination with highly accurate GPS produces 3D point clouds of area under observation. So in our case, it may be a tree. So this provides detailed information of a tree at the tree level or at the plot level. So this is not used for over a larger area. It has not been used. It is to give a detailed structure of a tree, or you can say a plot level thing, and it gives a detailed architecture or the structure of a tree. But it cannot be used for a larger area. Let's say for a district, for a state level, you cannot use for a larger area. This cannot be used since this is a ground-based instrument. Now, how do you work in field? So this is a instrument, is terrestrial laser scanner. This is a VZ Regal VZ400. Now here, this is a schematic representation of how we lay sample plots, how we scan in field exactly. So this is the front side of this instrument, where you can see this is the scanner here, and we have a camera also attached to it. And this is the back side of this, where you can see the scanning thing also. Now, the range of this instrument is 600 meter. Now, when you know, it is very easy to scan. When there is a single tree or standalone tree, you can easily, you know, scan. But when you are in a forest area, that means you are surrounded by trees in all the sides, how you will be starting your scanning. Now, let us say here I'm showing something like one plot area. Let us say this is a 0.1 hectare. So this is 31.62 meter by 31.62 meter this side. So we generally, you know, mark these corner trees with, you know, reflectors, strip reflectors. We mark these corner trees, and then from this position, central position, we scan the whole area. Now, since we are scanning from this area, and the, you know, range of this scanner is 600 meter, so obviously it will scan up to 600 meter. It won't restrict your the thing up to 30 meter or no, 31, whatever it is. So when you're scanning, so basically, first of all, you have to scan from the center, so it scans the whole thing. And one more thing, these red things, these are called circular reflectors or the retro reflectors. So these are placed in such a manner that when you are scanning from any area, the face of these reflectors should be visible from the scanning angle. So suppose so first of all, we generally scan from the center. We'll scan the thing. The problem is, suppose I'm scanning from here. So suppose this tree is behind this tree, so I won't get information about this tree. Moreover, when I'm scanning from this tree, there may be nearby tree, very near to the scanner. So this vertical angle is 30 degree by 130 degree. So I miss the top of the tree. So that means when there are more number of trees in an area, I have to have more number of scanners. So the number of scanning depends on the density of forest where you are walking. So, and the position also depends. So in addition to central scanning, I have to, you know, to scan 3 or 4 maybe in some cases from outside the plot. So it may be around 5 to 10 meter away from the plot, and from here I can see the scanning position should be such that from here maximum trees should be visible, you know. And so from here, so if I scan, I'll scan this part, and from here it will see the maximum contour trees. And whenever I'm scanning, and this I should make sure that this retro reflectors or the circular reflectors should be visible from all the scanning, because this will act as a tie point. When combined, when you merge the data sets, it will act as a tie point. So one central scan, and from outside we can have 3 or 4 scan, that depends on the area. So this is how it looks like in a similar thing I'm showing in a actual field. So this is, you can see these are the circular reflectors. These are the corner reflectors in field. Here you can see the strip reflectors, and these are the circular reflectors. These things. So I'm from scanning from here. This faces of these should be visible. And one more thing, when I'm scanning from any position, the position of these should not be changed at all. Only thing, you have to change the surface of the scanner towards the scanner. So this is how we scan. Once you scan, after scanning, so basically, when you're scanning from a center, you can scan in a horizontal angle of 0 to 360, full thing, and vertical angle is fixed for this instrument, 30 to 130 degree. But when I'm scanning from outside, this this outside means when I'm scanning, that view should be less. So I should not be scanning at 0 to 360 degree, because it will get additional things also what is behind me. So I can reduce this according to the situation or according to the view angle. So anyway, we'll be scanning. And one more thing is, like when you're scanning from outside, this should be around 5 to 10 meter away, so that the trees tops are visible with an angle of, let's say, vertical angle of 30 to 130 degree of the scanner. There is one more thing, like at the top of the scanner, there is a digital camera attached to that. So once you scan the whole thing, this camera takes photographs. Now overlap of these digital photographs, the overlap you can decide. Generally we take 60% overlap of each photograph, so it revolves 360 degree or the angle which I have fixed, and it takes a photograph. Now these images are basically used to colorize the point cloud data for better visualization during processing. That I'll show how it looks like, how without this photographs it looks like, and how with photographs it looks like. So basically here when I am scanning from center, this is the actual data of a forest area, how it looks in a from a center. So when you're scanning below the scanner, you won't get any information, of course, and this is how it goes. And these are the different position outside the your sample plot. Now once I get the data, I'll this is again one more angle, like this is from central scan, and these are from different points or different points outside the plot. So once I get this thing, so I need to merge all these four from center with center scan with scan position 1, and then with scan position 2 and scan position 3, so that I can get a 3D model of the forest. Now how do I merge this? Now it comes the role of this circular reflectors, which I was referring earlier. Now these circular reflectors act as a tie points. Similarly, when we mosaic optical images, we look for common features in both the image, and then we put tie points and then mosaic. Similarly here, the circular reflectors act as a tie point, so that I can mosaic, I can merge all these four and make a 3D model of the forest. Now this it looked like something like that, so that you can get a 3D view of the forest. Now once I move, so basically it will be like this. So this is a 3D, you can see here. So combining all this, I can get a 3D model of the forest. And now here comes the role of how this information can be utilized for biodiversity assessment also, forest biodiversity assessment. Because in this thing, you can you can see specifically what is there at the ground, what is the bottom trees, what are the tall trees, everything you can take care of. So basically these kind of inputs are very good when you are going for a forest biodiversity kind of assessment. Now this is not a photograph basically, which earlier I shot. These are without only this LiDAR point clouds. As I referred earlier also, like we take photographs and we take colors from these photographs and overlay this on this point clouds to get better visualization. Now this is a 3D model of the forest, and here we have put like the color from the photographs to get a better visualization. Now you can see the illumination condition, everything is visible. Now one thing is clear, like from this kind of data you can of course you can measure everything. You can get the height of the thing, you can get the diameter, you can get the spatial distribution of trees, and which trees are taller, which trees are at the bottom, which are at the at different positions which are there at that. So these kind of inputs are very good when you are going for biodiversity kind of assessment, forest biodiversity assessment. Now from this kind of plots or the as I said, it's a 0.1 hectare plot. From this plot, I can easily separate the different trees. So individual tree extraction is possible from a plot data. So basically, here you can see this plot data. We have separated different tree species here. There are different trees here. Now, one more thing is like now you can remove everything also from the surface and see that this white dots are basically the position of the trees. So you can see the spatial distribution of trees in a forest, or vegetation in a forest. Now these are actually height, height in meter, and this is diameter, in centimeter. Now here these are the position of trees. So basically you can see the distribution or spatial distribution of trees over an area, and this kind of architecture or structure you can get. Now these kind of inputs are very good when you are you are doing biodiversity study or studies which are related to, let's say, nesting sites, or studies which are related where uh, habitat studies where you need to provide the structural attributes. So these kind of inputs are very good, specifically when you are looking for a particular nesting site or some of the let's say bird species. Similarly, these are again a number like identification or the separation of trees from a plot level. So basically, from a forest, you are identifying or you are separating a small area, plot area. From the plot, you can separate the different trees, and you can measure also. You can get the measurement of height, diameter, then crown projection area, and these are the very good important attributes when you are going for forest biodiversity studies. Moreover, stratification also can be done. Now suppose this is the overall point cloud data. From this I can separate terrain, then I can separate the ground vegetation. So this is based on height, so all the structures I am getting, and then the low for the low height trees or the small trees and the tall trees. So this can be separated into these 4 components. Of course, it will be more based on the stratification of the forest. Now these kind of inputs are very good when you are very good input when when your study is related to forest stratification, or you are doing habitat mapping of some species, or you are looking for biodiversity studies, because here you can separate the center scan or the overall point cloud into different components like this: terrain, ground vegetation, small trees, tall trees, or you can have your own component based on tree heights, or you can separate seedlings, saplings, and then trees in a forest area. So this is about whatever I talked about terrestrial laser scanner. Coming to airborne laser system. Airborne laser system, the main component here is, of course, the laser scanner is there, which emits infrared pulses which reflect from the surface of the earth and object, and then this return pulses are recorded. And so there is a laser scanner, there is a GPS, and there is a IMU, inertial measurement unit, which gives precise orientation of the scanner. And this GPS gives precise location of the scanner. Now suppose this is a tree. Now if I send laser pulses, it will hit all these all these points. Of course, this depends on the density of the point cloud. Now density actually is decided prior to the flight. If you need detailed information of some area, the number of pulses per unit area will be more. If in some areas people prefer like 1 point per meter square for a larger area, but for if you are detail of a smaller area or detail attributes, or let's say height and structural attributes, will have a more number of points per unit area. These are decided before a flight plan. So suppose this, we are send laser pulses, and all these pulses hit here. Now all these points have a X, Y, Z coordinate here. All this point. So ultimately it will look like this. So basically from this tree, it will have this kind of thing here. Now here you can see all these. You can get a full structure of the forest here, and again, the structure of a single tree, and think of a forest, you get the full structural attributes as well as complexity in the forest, which can provide, and from complexity you can get an idea of a microclimatic variation, microclimate of these trees, and then a habitat of many species can also be studied using this kind of input. This is a satellite airborne. So this is basically rapid eye optical data, high resolution optical data, and then there is a airborne data. This data belongs to Nepal. Here you can see this these are called last points, and here you can see the vertical forest profile. Now this is a vertical profile of a forest. This is the whole data. I'm showing only a small part of it. Now you see these are the height parameters which are mentioned on the right side. So you can get all these height information. Suppose you want to classify a forest based on height, or you can get, this species is, up to this height, it goes up to this height, or this is beyond this height, you can identify based on height only. So basically, in addition to, let's say, optical data or optical 2D information, or based on some spectral indices when they are referred as an indicator of biodiversity, these could be additional things that will be going on that model or identification or assessment of this biodiversity. So here you get a total forest profile and structure of all the vegetation or trees in this area. So from this kind of data in the same area where I showed just now, so you can create the digital surface model. You can remove everything from the surface to get the DTM or the digital terrain model, and when you subtract DTM from the DSM, you get the canopy height model. So this is the canopy height model here. I'm not talking about here. So here you can see, wherever you click here, you will get the in the canopy height model. Wherever you click, you get the height parameter. So suppose so this is an additional information. You are getting about the structure of the forest, height of the forest. Now, when I'm saying DSM is basically this. This is the total digital surface model. DTM is this terrain model here only. And when I'm talking about CHM, I'm talking about this. So I am interested in this. So basically, from LiDAR data, I'll be able to extract a CHM like this, or canopy height model like this, and this could be a very good input for assessment of forest biodiversity. Similarly, coming to the third segment, this is called space-borne LiDAR. Now, space-borne LiDAR, that means the platform is your platform is satellite, and there is a satellite called ice cloud and a land elevation satellite, and the sensor was glass geosciences laser altimeter system. This operated between 2003 to 2009, and one of the objective also was to it had the capability, and people have done also studies related to forest canopy height and biomass carbon assessment. Recently, there are two missions were launched. One is the JEDI, Global Ecosystem Dynamic Investigation, and ISRO, this ice cloud and land elevation satellite. These are capable of estimating forest canopy structure. Now, this has a global coverage. I'll go one by one. Let us say first ISRO. This is of course is a NASA spaceborne satellite, and this is launched in 2018 September, and it is capable of directly measuring canopy heights globally and provide critical observation needed to improve our understanding of global carbon storm. Of course, now these kind of data sets again are since it is a global coverage, you can get a these data sets over over a larger area. And according to your requirement, let's say your requirement is habitat assessment of some species, or height or structure, you can utilize these data sets effectively for your study. Now, this satellite has a sensor called Advanced Topographic Laser Altimeter System, or ATLAS, and it operates in the 532 nanometer, and data is available from 14 October 2018, and this data is freely available. So so basically, if you see the specification of this, it stands around 10,000 pulses per second, and then this there are actually 6 beams. So 3 beams split into so basically there are 3 pairs like this, 6 beams and 3. So when you see the passes, there will be 6 on 6 in one pass. There will be 6 lines like this. So 3 pairs, and then every 91 days you will get a repeat pass of this, and the footprint is around 11 to 14 meter in diameter, and this is how it looks like. So basically, you can see there are 3 pairs like this, and there is weak beam as well as strong beam as well. So the surface which are low reflectivity targets such as ocean or land, strong beams are generally used, and beam spacing is like 2.5 meter along within the pair, and 90 meter across track within the pair, and 3.3 meter across track between the pairs. And every pair here, every pair will have a strong beam as well as a weak beam. Now they have different products. So these data sets, there are many products, but the products which is very important to us is ATL08, land, water, and vegetation elevation, as well as the ATL03, which is global geolocated photon data. So generally we use this ATL08 data. This gives directly the height. So whenever there is pass of this satellite and the point is there, or less a footprint is there, if you click this, the height of the you will get the height information about that forest. Forest. No. So I'll show from this. If you go to this data open altimetry site, you can browse this ISET2 data here, and then when you see inside these are the global coverages. Like here, suppose I zoom into my area. Let's say this is a part of northern part of India, and as I said earlier, also I mentioned there are 3 pairs. So you can see here like this, 3 pairs, and so whenever you click any of these points, you will get the height information. Suppose I click here, so I have selected from this data source only. I have selected a small part, and when I've selected this small part, you can see this. These are the canopy height estimates. So canopy height is around 30 meters, like 22, 25, 30 kind of thing over this area. So you're directly getting this kind of information from that open altimetry website of ISET2, and this is the surface elevation across this area. So this is very good recent information and good information. You don't have to process the data for getting the height and all, which we used to do in ISET1. Here directly they have given the product wherein you can get the directly height of the forest area. So using this kind of data sets, people have studied different habitats. Like here you can see forest experiencing logging, then intact tropical forest, and canopy height also have been canopy height map have been developed. Similarly, we have done a study wherein we have utilized this ISET2 point cloud data sets. ISET2 this data, this height information. Basically, we have integrated this with the Sentinel-1 data to generate the forest canopy height, and you can see this is a 3D view of forest. Now this of Dune Valley only. Now you can see here. It gives a total idea about how the forest or the structure of the forest looks like. Now, as I mentioned earlier, also in the initial part, also these kind of maps are very good when you are very good input for habitat modeling as well. Till now, what we do basically, we think of forest as a 2D kind of thing, and based on reflectance and other things, indices, we do this kind of modeling. But this could be additional information. Of course, the species in question has to be, or the target species has to be studied properly. If the species is dependent on the structure of forest, this kind of input will play a very important role. Moreover, these whatever this product is prepared is from free data sets of ISET2 and Sentinel-1, and of course using a free platform like Google Earth Engine. There is one more space-borne satellite. This is called JEDI. JEDI is called Global Ecosystem Dynamics Investigation. In JEDI, again, this is on board International Space Station. It again collects data, full FM data, and it operates in 1064 nanometer, and this is launched in December 2018. Uh, the footprint here is around 25-meter diameter. In earlier case, it was around 14-meter diameter. In this case, it is 25-meter diameter. And these are being used to create canopy structure, biomass, of course, and and the disturbance recovery studies also. This has the potential to study this kind of study as well. And here we have 8 ground tracks, basically 4 beams, and they are split into 8 ground tracks. So when you get the data, you get 8 ground tracks. And this kind of data could be very good when you are talking of, let's say, tree growth study, because there is a repeated coverage also, since this is the placeness of this JEDI as well as ISET too. But here you can see the tree growth, because there is a repeat pass of this. Then mortality also you can monitor. Regeneration status also can be studied, and competition of plants also can be studied using this kind of data, since these have temporal coverages. So this depends on, because this data set now is new, from 2018 we are getting data, but if it continues for, let's say, 10 years, we will be able to identify this kind of differences, let's say regeneration, competition. Or now also, after, let's say, within a span of 3 years, there is some change in forest. Let's say there is a disturbance in the forest, or there is a recovery in the forest. These things can be identified based on this kind of data, based on LiDAR data. So the science question which this JEDI tries to focus is, of course, what is the carbon balance of the Earth's forests? How will the land surface mitigate atmospheric CO2 in the future? And one more thing which is related to biodiversity is, how does forest structure affect habitat quality and biodiversity? We know that the habitat quality is directly related to the structure. So if we get an excellent idea of the forest structure, it will have a very good indicator of how good is the habitat is, and how it could affect the biodiversity. If there is changes in structure, structure which we can get through LiDAR data. If there is a changes in structure, how it will affect the habitat quality, and how it can address the biodiversity, or influence the biodiversity. The vertical forest structure plays a very important role when as I showed earlier also, and it is very much related to the biodiversity assessment. So using this LiDAR data, we get the best, let's say, structural attributes which other data sets won't be able to give, and we can relate this to biodiversity. Now, basically, what we do generally, we are talking for a smaller area when we take observation of a, let's say, 1 footprint or 2 footprints. Then we generally integrate with other parameters as well. Because these are footprints. You can see these are the footprints area. Wall-to-wall information is not there in case of what I showed in ISET2 also. There are passes. Of course, passes at different time periods. So there are but wall-to-wall data like airborne data is not. It is not like that. Airborne data, this is. So basically, we need to integrate with some other parameters as well to build a model for, let's say, in our case, we have generated a canopy height model over a larger area. What I showed earlier is we have integrated, let's say, JEDI with the other JEDI information or height information with Sentinel-1 data to get a overall a map of this area. And these maps are very good for very essential component, whether you can say, for assessment, monitoring, or monitoring, and of course for decision making. Recently, we have done one study with GRI data also in forest area of Portugal district of Uttarakhand. Here we have found that these, these are the satellite passes over the area, over the forest area rather. We have marked the non-forest area here. So here you can see these points. All these points have height information. Now, this is not a complete height of this, or the world-to-world height map is not there. Only thing, only what we have is the at these footprints there is height. So what we have done, we have integrated these height, with the Sentinel-1 data to generate a 3D model of this forest, and of course you can see the canopy height also, which varies from around 11 meter to 31 meter here. So you can see these areas where you have the tallest trees here, and these areas of course have shorter trees. Now here it gives you an idea of the structure of the forest, how the forest looks like in this area, and as I mentioned earlier also, this kind of maps, or this kind of inputs, let's say forest height map, these were not available earlier. Now you can generate this forest canopy map, and the studies, let us say we do habitat modeling of the different species. Let us say bird species or any species which is dependent on tree height. So when you were using earlier, we are using the parameters which are basically based on reflectance, or the you can say surface, or the indices we used to relate, but here now we can incorporate this height information as well. So when we incorporate this height information, and of course the species, the target species should be studied fast, whether it is related to the dependent on height or not. If yes, of course this new component can be added to get a better habitat attribute of the species, or the habitat modeling of the species. In addition to that, we can get the stratification of forest as well, like where the tall trees, where the tallest trees, whether the short trees, whether the ground, what is there in ground vegetation. This can be separated as well. More of the things you can, if you want to do a smaller area, you can go for a terrestrial laser scanner, and then using this, you can you can separate all these components. All these components you can identify, and in those cases, if you have detailed inventory or detailed structure of a tree, the studies like nesting, identification, nesting of birds and other things can be taken care of. So this is a map, global forest canopy height. This is also available. This is freely available. You can download this kind of maps already. One new version also have come up wherein the similar kind of thing, forest canopy height map has been generated for the whole world. But you can have your own map also regarding related to how you integrating the LiDAR footprint data, or LiDAR data, or height data rather, with other other data sets to get a 3D view of the forest. So basically, LiDAR's remote sensing, as we discussed, provides a 3D forest structure, which characterizes your vegetation height, vertical and horizontal distribution of forest. Although this LiDAR technology cannot be directly used for measuring biodiversity, but it has the capacity to give you an idea of the structure. And the previous studies have examined the hypothesis that vegetation structure is an important indicator of species diversity, as postulated by MacArthur and Adelin. So once you get an accurate structure of forest, this could be a very good indicator for species diversity assessment. Species distribution habitat models, as I referred here, built on LiDAR derived structural attributes. So in addition to your optical data derived variables, if you use LiDAR derived structural variables also, it will give a better representation of the habitat. And this technology could be effectively utilized for scientific and accurate means for forest management, for forest and wildlife management. This LiDAR technology, this is an important source of information for describing a natural environment in future. And as I mentioned, now we are getting data from freely available data from two space-bound satellites like ISRO and JEDI. So we are basically entering into an era of active remote sensing. Here I am only specifically mentioning about LiDAR only. So basically we are entering into an active era of active remote sensing forest with a wealth of upcoming data sets which are very sensitive to forest structure. Till date or till now, what we have is a recent data set is ISRO and ISRO and JEDI. And both data sets are available, freely available from 2018 onwards. So, of course, in the last 2-3 years, there's huge data sets, globally available, which can be effectively used for, biodiversity studies, habitat modeling, species distribution, and if you want, specifically for, let's say, studies like nesting, identification of nesting sites and other things, you can go for, terrestrial laser scanner. Airborne LiDAR scanner also have a very great potential. Only problem is whether data sets are available or not, because these are very sensitive data. Whether if data sets are available, these are excellent data sets because it gives, when I'm talking of airborne data sets, I'm talking of LiDAR. That means I'm talking of a centimeter level accuracy. So in that level of accuracy, you are getting the height information or the structure of the forest, which ultimately would be a very good input for forest biodiversity studies. So thank you very much for your patience for listening this lecture. Thank you.